Welcome to the short lecture series on reasoning-oriented retrieval. And in these slides, we'll basically build an understanding of reasoning-oriented retrieval through retrieval augmented generation and deep research agents. So we'll begin by discussing what reasoning means more broadly, including settings outside RAG. In particular, we'll be trying to understand RLHF, PPO, and GRPO to understand these ideas in detail. And from there on, we'll move to traditional RAG, looking at how retrieval augmented generation was approached before reasoning became central, and then gradually transition to reasoning oriented retrieval. And in the end, we'll also explore some exciting directions, including deep research. So, in order to motivate reasoning oriented RAG, let's try to see an example of a librarian and a user. A user comes to a library and asks for some book on some topic, and the librarian gets the top book that he finds nearby and gives it to the user. The user has not received the book that she wanted, so she asks again. The librarian then picks up the second book nearby and gives it to the user. Analogously, in a reasoning oriented search setting, when the user reaches out to the librarian first thinks about what are the possible topics that the user might like, compares different sources, looks at different bookshelves, tries to look through databases, talks to different librarians, and finally comes up with a book that he feels better suits the user. So, in this lecture, we are going to be focusing specifically on the second style of reasoning oriented search, where when you ask a complex question which does not have a straightforward answer, the librarian, or specifically our RAG system, obtains that answer via this complex multi-step reasoning search operation. Okay, so this is what we'll be looking at. We'll begin with traditional reasoning-oriented models in the non-RAG setting, meaning the standard setting, without retrieval. And the goal here is to understand how things have evolved from supervised, fine-tuned, instruction-following approaches to reasoning-oriented models, which often require some form of reinforcement learning. So specifically, we'll cover three approaches: RLHF, its supervised alternative DPO, and GRPO, that is Group Relative Policy Optimization. Once that foundation is clear, we'll move into reasoning oriented retrieval, focusing in particular on systems like Search R1, and use that to understand how retrieval systems evolve from a single step retrieval towards reasoning oriented search systems and deep research systems.
So, before we move on to the specifics, let's try to understand what is a typical uh, three-stage training architecture or a training pipeline that most of these frontier models that you interact with they follow. And typically, most of these pipelines have a three-stage process where there's an initial pre-training stage where you'll collect all web data, or you'll have a very large unlabeled set of data, web documents, which you barely look at, but you might do some basic filtering. But essentially, it's a large corpus. It could be like in GBs and sometimes in terabytes as well. It's often actually in terabytes. And post this, then there would be an instruction tuning stage wherein supervised task specific examples would be used to kind of make improve add capabilities to the model. So you could think of all the uh, popular natural language processing tasks like question answering, dialogue generation, and almost any tasks which requires um, a human written directly or indirectly human written examples to be used for training. So this is kind of the supervision stage. Um, there is a third stage, which called the post-training stage, which generally is used to impart reasoning abilities, which will be the focus of today. So that third stage, also known as post-training, which is either used to impart reasoning abilities as well as to make models controllable and safe. And generally, we're going to look at these three specific models. The first is reinforcement learning from human feedback, and there are two variations. one is PPO and the other is DPO. And here the human feedback would be essentially human annotators preferring one output over the other. So they'll be given like two responses, and they would be they would choose one over the other. So that would be kind of used as a reinforcing mechanism. And the other post-training algorithm would be RLVR, which is reinforcement learning from verifiable feedback. Specifically, we'll be looking at GRPO. And here, essentially, we'll have verifiable rewards. So essentially, you can imagine math tasks or simple question answering tasks, which require a lot of reasoning steps, but eventually have a short verifiable answer, which you can basically compute automatically and then use the rewards to basically reinforce. So we'll be looking at this third stage of post training in the subsequent um, slides. But essentially, the thing to keep in mind is that there are these three stages of uh, a typical frontier model that people generally use. That's a pre-training and the supervised fine-tuning or instruction tuning, followed by a post-training phase. And sometimes there's often a stage called mid-training as well, which is kind of in between pre-training and instruction tuning. And sometimes people also skip the instruction tuning section. So it depends a lot on how the performance of the model and what are the eventual where it's being deployed and so on. But yeah, but typically you would see like these three stages. So. So essentially, we'll be looking at these three stages of training ChatGPT. For instance, through the famous paper of OpenAI called Instruct GPT, and this is where essentially uh, there was an initial. There are like three steps here involved. The first step uh, involves collecting performing supervised fine tuning, which most of you are familiar with. The second step involves training a reward model and collecting preferences for it. And then in the third step, we basically use that reward model in order to reinforce or in order to post train our instruct tuned model. So we look at all these three stages, but as a start, we'll start with the first step of instruction tuning of supervised learning and how do we collect data for it. So, in modern natural language processing, especially before 2018, 2020, you could see that the focus of most of research of natural language processing was focused on these individual isolated tasks and uh, cause and effect relationship, named entity recognition, question answering, question generation. To some extent, that is true today as well. But the main point that I'm trying to make here is that much of the supervised fine tuning or instruction tuning training efforts went into curating such large collections of data sets. And there was a lot of benefits of collecting these data sets and training a pre-trained system like GPT-2 or GPT-3, and then seeing like massive gains across all of these tasks. So that was something that academics and people in the industry often did. And then there was this famous effort of Open Assistant, wherein a lot of researchers gathered together online and they started handwriting a lot of responses that an ideal conversation system should respond to. And there were other efforts as well for analog mentor, wherein people wrote Python functions which could basically scale and augment data in a crowdsourced fashion. And then came Alpaca, uh, in which the authors decided, let's take some seed instruction examples and let's use these examples to further bootstrap more examples from the language model. So there was a lot of efforts on creating these data sets more uh, very carefully and try to ingest these lot of reasoning patterns that we commonly would be either implicit to or we would rather not really specify them directly in text. So these are some examples of from the FLAN data set. For instance, can check like Ben and speaking with Herman, he suggested that you look at the earnings on Blue Dog on the and such, and then generate a subject line for this email. Uh, and the next one is like a few short example. There's a question followed by some options, then the answer is yes. The question followed by some options, the answer is yes. So there's you notice that there's a lot of these surgical changes or like these artificial changes being put into creating such form of data sets. And it might seem a little bit unnatural because we don't generally talk like that. We don't generally speak in a few short manner, or even from the point of view of models, it it's a very it is a pain point in terms of data collection as well, because that there's a large human explicit human dependency. So these data sets are not gathered implicitly as well. So there's that factor as well. um, so there's an example from Open Assistant, and you see the length of the example for like a question like explain calculus to a primary school student, and that's a pretty long response, right? So, and writing such long responses is really can be tedious and it can be super expensive as well. So there was a lot of effort, and such rewriting into longer responses or more complex responses. Uh, it gets harder and harder, not only with the length of the responses, but even with the specific topics that the responses, the tasks deal into, especially for like technical topics. For instance, it could be really hard to sit down and write almost like an essay long response for such a system. Yeah, so if we ask some annotators, for instance, maybe someone who's been around Emory to which is the best coffee spot around Emory, and should I invite my friend there? And we'll have these extremely mixed set of responses, and it's not a super ambiguous task, but it is there is a lot of still there's a lot of subjectivity involved in such a question. So getting annotated data in such a case would be extremely not only time consuming and having but you could imagine, like for instance, if you look at some of these responses, uh, it's almost all of these responses are not so unreasonable from the point of view of what we really get in large scale annotation data. So Caldi is the best because they have best lattes, but can be noisy. I don't drink coffee, so I'm not sure. So it's unclear whether we should include such a response or not. And something like no one will check what I wrote. So that's something that needs to be filtered out. So there are all of these nuances which come into picture, and there's a lot of cleanings and there's a lot of effort really involved into gathering such data sets. If you look at what GPT 5.3 would respond to such a question, um, the for instance, here on the right, we see GPT 5.3's response, and it is pretty complex. It includes a lot of bullet points, a lot of images. Um, it uh, it is kind of covering three coffee shops at least. Then there's possibility for follow-up questions. There's a map as well given, and you realize that the response is pretty long and pretty detailed. And trying to have such data obtained from human annotators is really hard and really expensive. So in order to gather much of these large-scale instruction-tuned data sets, we need to take care of a lot of things. Length and style. People generally prefer bullet points, and for instance, in the previous case, we had images as well, which decorated the answer. There can be implicit context, which can make things a little bit complicated. What are assumptions of people? Do different people have different assumptions? Do they agree or disagree on a lot of things? Uh, then there could be references as well. People would like to add references as well. Um, then there's a issue of scale. How much do we want? Do we want like 100 GB of data or 1 terabyte of data, or maybe just like a 10 MB of data. And this, all of this is just like focused on the capability data. That is how good it is on benchmarks of general task capabilities. But what about safety? So where will it be deployed? Whether it would be harmful, whether it would be biased, and so on. The questions related to that. One important thing to consider, for instance, is that models vary a lot in response length, and much of these benchmarks that we see have vary in the number of tokens used for the prompt as well as for the completion. So, for instance, here, if we see most of these data sets have like almost a very different number of tokens for prompt and completion. Some have like 71, some have 41, and goes up to even like 291. And so somehow the input prompt length defines how complex your task is. And completions could go also almost, there's almost all combinations here. So much of these data sets, they do have a complex variety. But if you look at how humans prefer, humans generally prefer lists, and humans generally prefer longer outputs. And this is something a little bit concerning, because we want to optimize for capabilities, we want to optimize for a lot of diverse things, but um, we do see that some of these things that humans find preference for are not really covered by existing data sets. So one possibility to address many of these concerns is to, why not take a complex data set? Why not take a data set which has complex knowledge, which is very factual and which has references as well? So, for instance, consider this example. Can you write a short introduction about the relevance of the term monopsony in economics? And on the right, we have a response, a typical completion, which defines monopsony, and in the end, there's a reference. So we use these as input-output pairs and use that to train a model. And what we are essentially asking the model to do here is like, one, we are teaching the model the concept of monopsony, uh, a complex concept, which is good. The other thing that we are also teaching the model is to output a reference or a citation at the end of the answer. So whether the what the model is going to learn is a bit of it's a bit of it's unclear to the model. So on one hand, it is possible that the model has some concepts in its pre-training data, pre-training distribution about monopsony and the reference. But if it does not have, what it's going to learn a pattern that anytime I'm asked a complex question, I need to end that with some reference tokens. And that is going to be a bad thing. Um, because the model will essentially learn to hallucinate, especially when we ask it some complex question. It will learn that, okay, whenever there's a complex question asked, I need to generate a long response, and in some abstract sense that response might capture some of the uh, aspects of the topic asked in some to some extent, but it will also end up in some form of hallucination. So this has also been shown in some other studies, which basically studied what are the how is the pre-training distribution versus this instruction-tuned data, how both of them, how the differences between both of them affect the way these facts are injected into the model. So, for instance, on the right, you could see like when there is when much of these facts are unknown to the model, the training accuracy is kind of slow initially. But when these facts are kind of known, so you kind of have these pre-training data has through web pages or through public content. It's if those facts are represented, your training is kind of faster and it's higher. And hence we need to be careful when we try to use um, the way we try to do fine tuning and what kind of data we use. And that is why John Schulman's recommendation was to um, uh, use some form of reinforcement learning to basically train only on those facts for which the model is already well aware of some of those facts. Um, and we kind of see that as well. Many labs in hence started this process of mid training, wherein they extend the pre training data or the pre training phases with an additional mid training phase, wherein they incorporate a lot of these reasoning tasks, which are or the instruction tune tasks, which are generally kept for the third stage. And we don't have to be not only careful from the point of view of just collecting data sets, but even the way we, for instance, do distillation. Because if we have a very strong teacher model, then there will be a big gap between the teacher model and the model that we're trying to train. And the same goes, for instance, when we collect human data as well. When we have long tail of very complex human data, but we have them in bits and pieces, they might not always help if the pre-trained model is not familiar with the facts there. Okay, so now we're going to come to the second part of the talk, which is reinforcement learning from human feedback, which is step two and step three, which we'll be looking at here. Uh, so to give, so first let's try to compare the supervised fine-tuning setting with the reinforcement learning from human feedback setting. So in the supervised fine-tuning setting, we have input-output pairs, P star y of x of some y given x, which is some model of the world. And that is some input-output samples that serve as a reference distribution. And we are trying to make our policy or our model as close as possible to this reference distribution by trying to imitate these samples. And hence sometimes SFT is also called imitation learning. Instead, and on the other hand, in the reinforcement learning setting, we are trying to optimize a policy, p cap y given x, to maximize the expected reward for a given reward function r y of x. So a typical SFT perspective or training process would have, apart from your base model, uh, costs for annotation, costs for feedback, and there will be a lot of costs for human written expert summaries. You need to gather experts, you need to make them write long outputs, and that takes a lot of money. Um, the other reason also why um, we need some form of reinforcement learning is because of how annotators don't really agree with each other. So we generally find that when we ask annotators to write down, for instance, language model summaries, they they generally disagree with each other about how good the summaries are. And more so interestingly, uh, many of these annotators, for especially for this specific study, they found that some of these annotators, when they wrote some summaries, complex long summaries, and then they compared those summaries to something written by ChatGPT, they themselves preferred the output of ChatGPT as compared to their own summaries. So you notice there's a lot of subjectivity involved in some of these uh, uh, data gathering efforts, as well as uh, gathering them has like expensive costs also involved. So and there is another reason why reinforcement learning kind of training would help search type of tasks and retrieval type of tasks. Because people generally care more about whether the search result solves their problem rather than how it was obtained. In fact, most users don't actively seek explanations unless the task is like complex or critical or high stakes. And many of these studies find that search quality is judged primarily by like the final outcome, with process being important only when trust or clarity is needed. Hence we are concerned more about really trying to optimize some ideal way of necessarily trying to optimize some ideal way of searching up information, but being able to reward based on how desirable the search outcome was. So now that we have enough motivation for using pairwise preferences instead of human written data, let's try to understand steps two and three, of the RLHF process. How do we use these pairwise preferences to train our reward model, and how do we use that reward model to finally train our policy? So here, essentially in step two, we would take our instruction tuned model and then generate different rollouts for different prompts, and this then ask annotators to rank these outputs. And then this pairwise data is collected and used to train the reward model. And then again, our instruction tune policy is optimized using RLHF or PPO specifically, which we'll look in the next slides, using the rewards generated from the reward model. So let's take a look at how pairwise data is indeed collected. So generally, annotators are shown two responses. You can see that AI response 1 and AI response 2, and a set of four-way outputs. That's it. Response 1 is better, response 2 is better, response 1 is slightly better, and so on. And annotators are also given detailed descriptions of uh, what type of annotations are expected. So specifically, the Instruct GPT guideline tells annotators to look at helpfulness, truthfulness, and harmlessness of model responses. So by helpfulness, they mean writing clear language and answering questions they are meant to answer. And by truthful, they mean there should be no hallucinations and the model's response should be factual. And by harmlessness, they mean the responses should not contain any unsafe or dangerous advice. Also, one has to be careful about the complexities of crowdsourcing. To get really high quality verifiable annotators, uh, it's hard generally, and it's costly as well. And many times annotators might not be motivated enough to check for things like factual correctness. And you might also have to be careful about any LLM use that annotators um, eh, may rely on. And at times you might be in situations where you might find annotators basically agree like 95 to 96% of the time with popular LLMs, and then you have to design some way of filtering out those annotators. So now let's talk about the methods. So now that we have hopefully high quality pairwise feedback data, how do we adapt our model to make use of this pairwise feedback data? So we're trying to find a policy that optimizes the expected reward for some reward function. And we look at what this reward function is and what this maximization process is. So here is the maximization objective from the Instruct GPT paper. And we are trying to sample some pairs x comma y from our policy pi. And then we are trying to maximize the reward function r x comma y. And then we are subtracting the KL divergence between our current policy and our initial supervised fine-tuned model so that our policy does not deviate too far away from our initialized model. And this gamma term essentially keeps a check by maximizing the log probability of the pre-training data to avoid catastrophic forgetting of pre-training. And this third term is not so often used, but the reward maximization and the KL divergence terms are almost used often. So what is the reward? So uh, we're going to look at this particular function, this particular equation. So there is this hypothesized model of the world, which says that every single model response of the world has some scalar value r associated with it. And we don't directly observe this r. So when a person annotates or when a person prefers one response over the other, they are essentially assigning a score to both of these responses and then taking a coin flip to which response is better. And we don't directly observe the score. This is like the Bradley Terry model of human preferences. So when we optimize a reward, what we are essentially doing is we are trying to output the sequence that has the highest R. And R is what is not what we directly observe. We observe noisy pairwise preferences. So let's now look at how we optimize our policy. And we'll be looking at PPO via this three-step process. And so when we try to optimize our policy, we are effectively maximizing the expected reward. And how do we maximize this expected reward? We take a gradient with respect to the policy parameters. And that is equivalent to taking the log probability of the policy weighted by the sum of the rewards. And this is essentially the reinforce equation that we see, which is a typical in a typical machine learning or reinforcement learning class. And then what is TRPO? Uh, so instead of taking the rewards, we maximize the advantage of our policy. And the advantage is essentially a variance reduced version of our reward. And so what we are taking here is we are taking the reward and subtracting a baseline, also called baselining, and that it still satisfies the reinforce equation, but uh, but there's an added benefit of that it reduces variance and makes training stable and efficient. And we also want to take multiple gradient steps. So uh, once we update our policy, and hence we allow our policy to go a little bit stale in a controlled fashion, so that we can generate multiple rollouts from this older policy while we are still updating our newer policy. And this basically multiplicative factor, also called as policy correction, makes that possible. And TRPO applies this trust region constraint to limit how much the policy can change, ensuring that you have stable updates and monotonic improvements. So finally, PPO, the PPO loss function takes in this scale constraint and then bakes this directly into the loss function through a clipped objective. And this clipped objective discourages large policy updates by discouraging anything which is outside an epsilon neighborhood um, region. So there were many efforts to try to make a supervised equivalent of this RLHF PPO objective, uh, and not many successful efforts. But one of the most successful attempt was DPO, direct preference optimization, and DPO was able to get rid of the reward model as well as get rid of a lot of on-policy stuff like the rollouts and the policy correction. And DPO made it possible to essentially use these preference pairs, human annotated preference pairs, to fine-tune a language model in a supervised fashion. So we simply take the gradient steps on the log loss of good stuff and take negative gradient steps weighted appropriately on the bad stuff. So let's quickly look at deriving the DPO formula. So what is our goal? Our goal is to optimize this quantity on the top. Uh, this is the PPO RLHF equation written as a maximization objective, which has the reward function term and the KL divergence term. And DPO makes this assumption, non-parametric assumption, assuming that this policy necessarily does not come from a neural network, but is an arbitrary policy of any kind. And if we do that, we are able to define what the optimal policy is, which is the second equation, which is and the optimal policy is essentially can be written as the exponent of the reward multiplied by a reference policy. And now, under this non parametric assumption, instead of thinking about the policy, we can think about the implied reward. So we can take a look at the gradient update of DPO. Uh, there's this beta term, which is the regularization term. And what this equation is doing is it's taking large gradient steps when the reward estimate is wrong. And that is what this first logistic term is doing. And then there are these two terms which basically represent increasing the likelihood of the good example as well as decreasing the likelihood of the bad example. So implementing DPO in this supervised fashion definitely made it easy for many to implement and try out various experiments. And hence, there were a ton of papers on DPO variants like SynPO and length normalized DPO and so on. Uh, for instance, SynPO made these two small modifications. Uh, they normalize the update size by the length of the response, that is the uh, denominator in blue. Um, so here, the theoretical argument is kind of lost because they've removed the uh, reference policy term. But uh, but this equation does have this nice form of upweighting the good responses and downweighting the bad responses. Um, there were other variations like length normalized DPO as well, where they removed the reference. They did not remove the reference policy, but they still apply normalization called length normalized DPO. And most of these methods did work quite well. So now we look at a third and an exciting popular paradigm um, called reinforcement learning from verifiable feedback. And specifically, we look at GRPO, which was introduced in the DeepSeek math paper, and which was later, then in different ways, was also adapted by different frontier labs, and more prominently by DeepSeek R1, Kimi 1.5, and Quen, and then many others. So, why do we need another reinforcement learning algorithm? Why not PPO or why not DPO? Uh, we would like to be able to apply to tasks that PPO is applicable for, but PPO is extremely expensive, and PPO requires a separate value model to compute the advantage estimates, and that means we we require double the number of GPU resources, one for the policy and one for the advantage. Um, DPO, on the other hand, is designed with the Bradley-Terry pairwise structure in mind. So if you would like to extend to other tasks, like solving math equations or searching and obtaining a short answer from the web, we don't really have a preference structure of our outputs. So here we come to one of the most influential and exciting approaches of 2025, that is GRPO, or Group Relative Policy Optimization. And GRPO is pretty simple. Conceptually, it's just like PPO. So here you have your first term, which is the policy corrected reward maximization term, and along with a KL divergence term. Um, so what is the unique advantage of GRPO is that GRPO gets rid of the costly advantage computation or the value function that is used in PPO. And instead, what they define an advantage through group reward. And so here the advantage, for instance, for a response I is the reward obtained by response I minus the average reward uh, received across for all the responses in a particular group, and we'll define what that group is, divided by the standard deviation of that group. So the advantage for a response I is like the z-score of the reward estimate. So now, what is a group? So specifically for each question or each example, input Q, um, GRPO essentially samples a group of outputs, capital G, O1 to OG, and then computes the advantages within that group. So know that this group is essentially it's not related to the batch size, where we look at multiple queries. Here the group is essentially different rollouts of the same query. And hence, this normalization also within group makes sense. So, for instance, some math problems might be harder than others, and hence averaging with respect to um, the same input makes sense as kind of considering the difficulty level of each of the individual problems. So essentially, that is what GRPO is. It's taking the costly value function and replacing that with this advantage estimate, which is just obtained from a group of multiple rollouts of the same query. And one last thing. So if you take the pure online case, we basically get rid of the clipping term, and basically we are left with maximizing the advantage. So the equation becomes way more simpler in that case. So how do the results look? So GRPO works pretty well. And here are the results from the DeepSeek math paper on two math benchmarks, GSM 8K and math. And so two different GRPO variants are compared, GRPO outcome level reward and GRPO process level reward. So essentially in the process level reward, you assign rewards for each of the individual steps of a rollout. And in the outcome level reward, you only assign the reward at the end. And these two variants are found to be better than uh, RFT, wherein they train on rollouts which the policy got the answer correct. And they also find that process level rewards are uh, help as compared to outcome level rewards. So one of the first retrieval augmented generation approaches in papers like Realm and RAG for knowledge intensive tasks used a single step of retrieval to generate the answer. So here what we essentially did was we took the query as input. A query encoder like BERT was used to compute similarity with a large number of document embeddings, and subsequent classification or generation was conditioned on this document embedding. And the generator was trained using classic language modeling approaches like mass language modeling. And some of these approaches also backpropagated to update the query encoder, and at some frequent or infrequent intervals, the document embeddings were also updated with the updated encoder. However, most of these approaches used a single step RAG approaches, wherein retrieval was just called once using the original question as the user query. And this meant it was hard to answer more complex user questions, which would require multiple retrieval calls, like when information sources were spread across multiple documents. IRCOT introduced an interleaved reasoning and retrieval loop. So instead of retrieving once, the model first generates a small piece of reasoning, that is, a small set of reasoning tokens, like a partial chain of thought. And that intermediate reasoning is then used to form a better retrieval query, which brings in more relevant evidence. And then the model continues reasoning, retrieves again if needed, and repeats this process. So the authors find that interleaving reasoning with retrieval significantly improves both retrieval quality and the final answer accuracy on multi-hop tasks. And they found that that improves as compared to one-shot retrieval, wherein a single query is used to retrieve documents. And there were many papers which perform multi-step retrieval, especially in open domain QA, right from 2019, 2018, possibly before that as well, um, before chain of thought and reasoning chains were common. And this is an interesting one or interesting paper because it does that by interleaving the chain of thought tokens with retrieval. So approaches like IRCOT were used during inference time. Instead, in Toolformer, the authors trained the LLM to generate such tokens. So in fact, they generalized to some more tokens apart from search, like a calculator or a calendar API. So what they essentially did was they first artificially generated training data. So they took general text, and then they substituted an entity with an API call. So they only substituted with an API call if the subsequent token losses were reduced by keeping the API call. So in the right figure, you can see how a QA tool call is inserted. And during runtime, whenever such tool calls were generated, the generation was paused, a retriever was invoked, and the resulting answer from the retriever was substituted back instead of the tool call. So in that way, the LLM had complete control of calling external tools by just generating these tool tokens. Now we looked at RL approaches like GRPO in the context of math and logic problems, and we also looked at tool former, how it used supervised fine-tuning in order to generate search calls. In the math and logic problems of GRPO, the task was simple, at least from the point of view of design. We had a question and the policy generated rollouts, and then depending on whether the rollout gets the correct answer, GRPO gave a reward of 1 or 0. So in that setting, when your task doesn't require information, in that setting, the task does not require information from outside of the weights. Now, in this approach, search R1 or research, the approach is not much different, except that the policy rollouts can now make external calls to a search engine or a retriever, just the way we saw in Toolformer. And how they do that is by defining a template to instruct the model to generate search queries through search tokens. And during the rollout generation phase, whenever you encounter a piece of text enclosed in these search tokens, you pause, call a retriever with the query, and then come back and append the retrieved passages through these information tokens. And then continue the generation until you generate the final answer. And what is the reward? The reward is simply 1 when when the answer in the answer parentheses matches your ground truth. So let's try to look at it again once a little bit carefully. We have our input query X, our policy model, uh, some search engine or a retriever, and a maximum action budget, which will restrict the number of retrieval calls that we can do. We start generating tokens from our input and whatever we have generated till now. And if the new token is basically an end of search token or an end of answer token or an end of sequence token, then we break. Else we continue to generate these tokens. Then we check if we have a end of search, start of search and end of search tokens in our complete sequence. If we have that, then we extract that to get a search query. Once we get the search query, then we call the retriever, get the document, and insert the document back again in our rollout enclosed in the information tokens. Or else, if we have answer parentheses detected in the rollout, then we return a final response. So one important thing worth glossing over is the loss masking for retrieval tokens. So in GRPO, once the model generates the rollouts, we compute the loss over the tokens of the rollout sequence and then multiply it with the reward and then perform policy gradient. But now in these rollouts, in search R1, we have tokens from external passages as well, and they might have a completely different distribution than our policy model, and that would affect training dynamics. And that is what the authors actually observe. So the authors, they do an interesting thing. They mask these retrieve tokens during loss computation and find that that actually improves training stability drastically. So you can see search R1 with mask has an average of 0.431, but search R1 without mask, the average score decreases. And they find that for two different models as well. So in a nutshell, you can understand the kinds of behaviors you can train with such a setting like Toolformer or Search R1, and one can extend this to end-to-end training to perform tool calling or any sort of tool calling, for instance. So along with Tool Former, Search R1, and a couple of other papers, there were many papers which tried to have subsequent works, and they were all very interesting. For instance, one is R1 Searcher. Uh, R1 Searcher used reinforcement learning to train in a for this multi-hop QA rack task in a phased manner. So it was a two-stage manner. So in the first stage, they trained a policy with a retrieval reward and a format reward. So no answer reward like search R1. And the retrieval reward does not necessarily actually check for retrieval effectiveness. That is, it does not check how good the external evidence is or how what is the ranking of the evidence, but it just checks the number of retrieval, whether whether more than one retrieval call was made. So if more than one retrieval call was made, then uh, um, a reward of zero point 0.5 is assigned. So this was the first stage. So the first stage just ensured that made the model familiar to make retrieval calls. And in the second stage, they got rid of this retrieval call and they just used the answer reward and a format penalty. So the essence was like a two-stage curriculum. The first stage made the model familiar to make retrieval calls, and the second stage made the model basically try to get the answers using those retrieval calls correct. As GRPO started becoming more and more popular, many people also tried to train policies with GRPO for different standalone retrieval tasks as well. For instance, there was this paper, Rank R1, which trained a re-ranker, that is a second stage ranker, using by GRPO-based reinforcement learning. So here is what they actually did. So they started with a first stage retriever like BM25 to get the top documents, and then they constructed a set-wise ranking task, which was popular through previous approaches, where the model was shown essentially multiple documents and asked to pick the most relevant one. And so they modified the prompt to force the model to generate these reasoning tokens first and then output the final document, which is the top ranked document. And the reinforcement learning reward, or the reward used for GRPU, was just the exact match with the document ID. So here you see how GRPO is used to implicitly learn better reasoning patterns or reasoning processes for ranking or re-ranking decisions. So let's try to take a look at the prompt of rank R1, how they've exactly used for re-ranking. Um, so here you can see, uh, given the user query, which of the following documents is most relevant, and they provided documents as a list, document 1, 2, and so on to document 20. After completing the reasoning process, please provide only the label of the most relevant document in the query enclosed in square brackets. So, for example, if the third document is the most relevant, the answer should be open think, close think, open answer, bracket 3, and close answer. So this last document ID would be used for as a verifiable reward. On the right, they've also shown a sample example of how the GRPO trained one got it right as compared to a zero-shot rank R11. So Search R1 and Research showed performance improvements on multi-hop short question answering like Hotpot QA, 2Wiki QA, and here the final answer was like 2-3 words long. So you could still evaluate the final answer fairly directly. But then there were some other papers which extended this in various ways by defining novel reward functions and training strategies, especially for long form generation tasks where exact match would not really work. So essentially, by simply designing your reward functions, you can imagine like the number of tasks that you can extend such a framework to. So O2 Searcher, for instance, here they performed question answering for long form tasks, and hence they rewarded rollouts for format correctness, diversity, and factuality. R search was also an interesting approach. So they added an explicit evidence generation step where they not only inserted retrieve tokens but also generated summaries from those retrieve tokens. And for the answer reward, they essentially measured the quality of the evidence being retrieved. and they take the generated essentially they take the generated evidence and feed it to a different family of frozen model and have that model basically answer this question using this generated evidence and see whether that is similar to the gold answer. If that is highly similar, that means the evidence is very useful. So you can see essentially how any policies, both RAG as well as non-RAG, were rewarded by using feedback from external models or even sometimes LLMs as judges. So you could uh, basically expand the number of tasks that you could address. Okay, so now we come to the last part of the lecture, which is the school functionality of deep research. And so I'm sure till now most of you have used deep research as a feature, and especially through frontier systems like ChatGPT and Gemini having an explicit button for it. So we saw previously how models were trained to perform search, and now we look at similar systems which are trained at a more trained or prompted at a larger scale. So what is it really deep research? So it's not much different from what its name actually implies. So generally speaking, it's the ability to answer queries using information that is really hard to find in your document collection or hard to find over the web. And you can look at some of the sample queries here from the browse corpus. For instance, the first one, as like between 1990 and 1994 inclusive, what teams played in a soccer match with a Brazilian referee, had four yellow cards, two for this, and so on, so on, and one of which was an injury in the first 25 minutes of the match. And the answer is Ireland versus Romania. So questions like these essentially um, test a lot of different abilities. They require, first of all, asking multiple queries. And when asking multiple queries, the model has to generate these queries themselves. So there is a test for query reformulation. Then there's a test for strategic perseverance, or basically how well um, the model orchestrates such queries, what queries it asks first versus what it asks last, and what kind of queries it generates. And more importantly, especially for deep research, report generation, how is the ability to assemble these fragmented clues together and generate a very coherent report. So, um, in the subsequent slides, we'll be focusing more on the retrieval side or on the starting side of how these documents are collected. And if there is time, then we'll also cover the generation side of it. So there are benchmarks that let us evaluate these deep research capabilities. And one important one is OpenAI's BrowseCom benchmark. And it's important to understand how they built this. That's pretty interesting, both from the perspective of how to design a deep research agent, as well as in general to understand how these data sets and benchmarks are created. So, what they did was pretty interesting. So, they asked annotators to start from a known fact uh, or an answer and then work backwards to write a question. And so, a question that would be hard to solve but easier to verify. So, the annotators already knew the target answer, but they had to phrase the problem so that finding the answer would require persistent, creative web browsing rather than just a simple single step search. And because the answer was designed to be short and some sort of an indisputable fact, evaluation became much easier. So it became verifiable. So you don't need to judge a long essay or open-ended response. You can simply check whether the model gets the exact short answer right or not. And when humans were asked to solve these tasks, they found them um, genuinely time consuming. For solvable questions, humans took about 2 to 3 hours, sometimes even 4 hours. And for unsolvable questions, they mostly gave up after 2 hours, as you can see. And another broader lesson to understand here in creating such benchmarks is often how they make use of this asymmetry of verification. So what this means is that some tasks are much easier to solve than to verify. And if annotators begin with a known fact, they can craft a question whose answer is absolutely checkable, but whose search path is non-obvious, but it's like more targeted, but a bit complex. It requires a lot of going around to different web pages, traversing a lot over the web, and then finally coming to an answer. So this benchmark ends up testing not just like recall, but persistence, search reformulation, and the ability to be able to connect these clues across different sources, which is what we saw for a typical deep research benchmark. So, Browsecom's performance on models, let's see that. So, at least as of mid 2025, which might be, let's say, 10 AI years behind, the headline is that the benchmark is extremely hard for ordinary models. OpenAI reported at that time that GPT-4o scored 0.6%, GPT-4o with browsing scored 1.9%, and GPT 4.5 scored about 0.9%, and O1 scored about 10%. And their deep research system, which was essentially a system exposed with many training examples of this sort, that did 51%, which is still far from perfect, but dramatically way ahead of the others. And this result suggests that simple access to browsing is not enough. Like what matters is whether one can systematically do this browsing, and one can be persistent, be able to ask the right or generate the right reformulation queries, and basically recognize like which reasoning paths or which search paths are promising. The authors also found that performance scales with respect to the amount of compute used. Uh, so as you increase test time compute, or as you increase the number of thinking tokens during inference time, performance increases almost linearly. Um, oh, sorry, it's a log scale. So it does improve with increasing number of tokens. And one of the other strategies that also improve performance is using some form of self-consistency, and which you'll often notice in many tasks and not just deep research. Um, like there are a lot of other multi-hop question answering tasks and even math-based tasks also benefit from this form of self-consistency based aggregation. So here they generated 64 different outputs. They sampled 64 different outputs per question, and then they asked the model to output a confidence score. And then they applied three aggregation strategies. Majority voting selected the most frequent answer among the samples. Weighted voting, zero shot prompts the model and gives a confidence score for its answer, and weights each vote by the model's confidence. And the best of n selects a single answer with the highest confidence score across all samples. So all of these approaches basically benefit by 15 to 20% as compared to just using a single attempt. So OpenAI's browse comp was is a very useful uh, benchmark, but it's operated over the web, and that means uh, results might vary, especially across longer time spans, and hence sometimes it might be hard to basically have reproducible results. And so some authors basically came up with this another benchmark with retrieved documents which would stay in your documents which would stay in your local system, browse.com plus. So basically it's a retrieval benchmark just like ms marco trek and other popular retrieval benchmarks. And so how they build browse.com plus is also interesting. So they start from the original browse.com questions and answers, and then they try to reconstruct the evidence behind each answer. So first they use a strong model like O3 with web search to find supporting web pages, and then they break the question into smaller clues that justify the answer. And then they get human annotators to essentially go in and verify everything. They check whether the documents truly support each clue, label the exact evidence spans, and even search for additional documents if needed. And that gives them high quality, verifiable evidence. So now this essentially works like a retrieval benchmark. But generally, in creating such benchmarks, people often add hard negatives as well to test the ability of the retrievers under distracting documents, also called hard negatives. So here also for each question, they decompose it into similar sub questions, and then they run a web search to collect documents. And basically, these are distracting but plausible pages. So in the end, each question has supported highly relevant documents as well as irrelevant or hard negative documents. So now when they evaluate these models on this setup, the results are also pretty striking. So strong proprietary models like GPT-5 massively outperform open source search agents. For example, Search R1, which is specifically trained for search, only gets around 3 to 10% accuracy depending on the retriever. So they use BM25 as well as a Qwen 3 embed 8 billion uh, dense encoder. And um, GPT-5 reaches about 70% when paired with a good retriever. And what's really interesting also is that this gap isn't about knowledge. It's more about how well can the model iteratively search, reason, and use these search calls or use these tools. So, um, so BrowseCom Plus, the main takeaway from BrowseCom Plus is that current open source agents are still quite limited compared to stronger models, especially in this deep research kind of setting. So now most of the architectures we looked at previously look to solve problems through the granularity of operating over a single model, training input output pairs and testing them to see performance. But now, as models are becoming more capable of excelling at various tasks and are able to reason, um, we move to the more popular agentic view where we can achieve many tasks through simple prompting itself. And uh, also, however, as tasks get more complex, we can try to break down these tasks into smaller tasks and try to solve them. And that's what these high level agentic patterns essentially attempt to do. So, how do you design these agentic patterns depends on your task of interest. That is the particular domain you are in and the capabilities of a model. So, smaller models may probably require more breakdown of tasks than larger ones. But more generally, here are a couple of agentic patterns that people often use more or less for many of the tasks. For instance, in the chaining or the sequential patterns, we decompose a task into ordered steps where each model feeds into the output of the next. So, for example, writing, editing, and summarizing a blog post would probably be a task like would be used for uh, will use an agentic pattern like prompt chaining or a sequential pattern. In the routing system, the system or an orchestrator kind of decides which specialized model or prompt path to use based on the input type or the intent. Example, customer support systems or routing bill queries to a finance agent and routing maybe technical issues to a debugging agent. In parallelization, multiple subtasks are executed simultaneously and the results are later combined to have a final answer. So this is analogous to self-consistency. And so we generate multiple candidate answers or search answers and search results in parallel and then re-rank them using classic retrieval paradigms like document fusion or perform multi-query retrieval in RAG. Um, in reflection, the model critiques and iteratively improves its own output before producing the result. Um, this is often seen in code generation models, where models try to perform self-debugging or test case checking. That is, write code, review, and then check. If the test case fails, then again try it again. In tool use, of course, the model augments its capabilities by calling external tools such as search, calculators, or APIs. And in planning, an agent often has there's an orchestrator first, which creates a high level of subtasks and then assigns each subtasks to specific expert agents. So it's possible that, for instance, one agent writes, another reviews it, and the third tests it. Or it is possible that we might be interested in a system which has multiple personas across different agents. So we looked at different agentic patterns where much of these workflows or these different agentic patterns were designed by humans itself. But tasks may not always need to be defined by the human workflow designer. And these task breakdowns may often emerge as a part of the reasoning trace of a single agent, and the model itself may autonomously attempt to break down and solve them. So, for instance, there's this interesting study in which the authors of this Cognitive Foundations for Reasoning paper, they took basically a bunch of tasks and tried to look at their chain of thought reasoning traces of some popular models, and they checked if cognitive elements are present in these reasoning traces. By cognitive elements, they mean essentially the way there are these different patterns of way, how people solve, how humans in general solve problems, and these are all uh, these cognitive elements which have been discussed in the psychology and the cognitive psychology literature over the last 20, 30 years, or even before. So uh, and what they concluded that for task successes, it's not necessary that models may need to follow human-like thinking process, and often there's less overlap between cognitive elements that humans and models use. So this is not so unsurprising. It is kind of, to some extent, it is also a little bit of bit obvious that we need not have an optimization or a path that hu- already humans have done, and we just basically try to have that as the optimal path. That is the risk of anthropomorphization that people often talk about. Uh, but many of the patterns, like reasoning chains, for instance, are something unique to language models, which are less talked by theory, less inspired by theory, but are more emergent. And much of these models are also performing well because much of these patterns are also available over the internet. So it was an interesting study. This is an interesting study. So the main takeaway of this message is that the main takeaway message is that it's crucial to be able to get a sense of how much hand holding is required when designing these agentic patterns versus how much we should allow the model to do autonomously.